All right, so I'm gonna start. I hope you can all hear me. All right, so this tutorial is gonna be about optimal control. So this is going to be the last tutorial in the optimal control series. And we're going to talk about trajectory optimization. And most of the slides are based on notes and lectures by Dr. Matthew Kelly and Dr. Ross Frederick. So Matthew Kelly was, he did his PhD at Cornell with Andy Rowena, mostly on legged robots. So he did a lot of trajectory optimization. And during his PhD, he wrote a bunch of tutorials for trajectory optimization, which are like really cool. Yeah, like the standard tutorials for trajectory optimization. And after his PhD, he worked at Rethink Robotics, and he was also a professor in my college, my undergrad college. So I had some first-hand experience with him. And then later on, he left to Boston Dynamics. So he's currently at Boston Dynamics, and he works on the Atlas robots. So he does trajectory optimization for the Atlas robot. So he's definitely legit. And some of my slides are also from Ross Frederick's lectures, and Ross Frederick is a professor at MIT. So why do we need trajectory optimization? So just as a recap, in the past few weeks, we've been talking about optimal control, basically how to get the optimal sequence of actions in order for a robot to enter into some goal state or some desired state. And the first way we talked about getting the optimal sequence of actions was through dynamic programming, and specifically through using the value iteration algorithm that basically computes the cost to go from the goal state and backs up all the way to all the other states in the world. And so it ends up returning a policy, and that policy, the optimal policy, basically is a function that maps states to action. So it basically tells us that if we had some particular state, what action should we take in order to end up in the desired state. And the nice thing about value iteration was that it works for arbitrary dynamics. We don't really think about the dynamics of the system. All we need to do is think about how to discretize the system, and also think about an additive cost function that would enable us to compute the optimal cost to go or optimal value function for our entire domain. And so how we basically solved it was that you get a domain or a system dynamics, and we basically apply a mesh on the dynamics. And the mesh is basically to discretize the domain into some discrete states. And at once you realize that if you are discretizing the domain, then it means that it's most likely going to mean that we wouldn't be able to do this for high dimensional systems, because for high dimensional systems, the number of states would basically be exponential with the dimensions if you're going to perform discretization. If you're going to discretize the entire state space, then the higher we increase the number of dimensions, the more computationally intractable our value iteration becomes. And so experimentally, you realize that after above dimension 5, that's if your system has more than 5 dimensions, it becomes infeasible to actually use value iteration to solve your problem. At least with the dynamic programming value iteration. I mean, you could probably use neural networks and that could probably work, but for this formulation of value iteration, it's probably not going to work for higher dimensional systems. And so that was a real bummer, because most of our systems are usually high dimensional. For instance, if you want to get optimal controls for a humanoid robot like the Atlas robot, which has 36 dimensions, it's going to be difficult for you to, you can't basically discretize every single dimension and use value iteration to solve it, because that's going to be infeasible and not possible. And so so this was covered in the first week. And in the second week, we looked at a way of coming up with an optimal controller for higher dimensional states. And we talked about the Hamilton-Jacobi-Bellman equation and the linear quadratic regulator. So the linear quadratic regulator was nice because It enables us to perform optimal control for extremely high dimensional systems. Like, we weren't constrained by the dimension of the system. And we also talked about how it was actually used in MIT's entry into the DARPA Robotics Challenge 6 years ago now. Yeah, that's in 2015. They used a lot of LQRs for basically controlling the robots. And so it tells us that LQR is really powerful. But then LQR comes with two major conditions. So the first condition it comes with is that your dynamics should be linear. So your description of the dynamics of the system should be a linear system, meaning you should have the dynamics equation should be linear in that it should be basically made up of some AX plus BU, where A and B are some matrices that represents the states, as well as that's for A would represent the states, as well as B represents the weighting of the controls U. And so we talked about how so that was like the first condition for LQRL. It should have a linear state dynamics. And the second condition is that it should also have a quadratic cost. And the reason why it has to have a quadratic cost is because the cost should be quadratic in terms of the controls and the states. And the reason is that the optimization procedure used for coming up with the optimal controller for LQRLs makes the assumption that we can perform convex optimization. And so because we want to perform convex optimization, our cost function should be quadratic with respect to the states and the control inputs. And so that was also a limiting factor for LQRL. So for states, or for for dynamical systems like say the Atlas, where it's definitely nonlinear, the dynamical system is definitely nonlinear. What you usually have to do is that you linearize it using some first order Taylor expansion. That's in the second line of this equation. Basically linearize your dynamics such that you linearize it at a specific point, or the region where you want to act. For instance, if you want the optimal control for a state X prime or something, so for some state X, in order to get the optimal control at that state X using LQR, you basically have to linearize the dynamic equation of that system at that point using a Taylor expansion, first order Taylor expansion. And that will give us a linear equation with which we can then use LQR to solve for the optimal controller. And so that was the that's the drawback of LQRL. We basically have to be linearizing all the time. And so the controller you end up with is mostly going to be pretty good at the linearization region. So if you linearize at some region or some state that's X, your controller is going to be perfect for that state and surrounding regions. But then as you go further from that state, you linearize it at, your controller is going to be terrible and much more and more terrible. So in order to, so for each state, you basically have to re-perform the linearization, and that might not be optimal for tasks that require like a longer sequence of actions. For instance, if you want to plan a trajectory from some initial state to some goal states, say if you're a Quadrotor and want to get an optimal trajectory from some start state to some goal states, the trajectory is going to be made up of multiple states. And so you could end up having to linearize at each point, which is actually what's performed by iterative LQR. You could actually get that to work, but then LQR in its current form will not be able to work for such a task that requires a longer trajectory. And so, given these two drawbacks of the last two approaches we've talked about in the last weeks, trajectory optimization basically tries to address these three problems. And so the nice properties of our trajectory optimization is that, one, it works for higher dimensional systems. So it's agnostic to the dimensions of your system. So you could be dimension 4 or dimension 40 or 50 or whatever. It's still going to work because it doesn't scale with the dimension of the system. So that's the first benefit. And the second benefit is that because we are optimizing an entire trajectory, we don't necessarily have to linearize at a specific state. we can come up with, we can output an optimal trajectory that's like optimal for a longer sequence of states, and that's also nice. And how is it able to actually get these benefits? So the main points trajectory optimization tries to prove is that the case of dimensionality is not really a problem. So the case of dimensionality basically states that as the dimensions of a state space increases, it becomes more and more difficult to come up with it becomes more and more difficult to solve the state space or to come up with optimal sequence of actions to take. But trajectory optimization basically avoids that problem by saying that when you actually think about it, we don't really need to get the optimal control inputs from every single state space in our state space. We only need to get the optimal trajectory from some start states along some specific trajectory to some goal states. So we don't really care about what happens in other states we don't visit because that's not relevant to our task. If the goal of the quadcopter is to fly along some trajectory or fly in some way to get some goal states or some goal position, it doesn't really care about the best control it should take at some states that are like outside the room or that are not part of its state space, or even if it's part of its state space, that are not like relevant to the task it's trying to accomplish. And so that's how trajectory optimization avoids the complexities of or the drawbacks of both value iteration and LPRL. It basically plans from a single start state to a single go state, and that makes it pretty good for kinds of problems it tries to solve. And so what exactly is trajectory optimization and how does it work? And so the next few slides were from Matthew Kelly's tutorial on the topic. And so yeah, this is how it is. So as I stated earlier, on the left is basically value iteration, where it basically discretizes the domain into discrete points and then finds the optimal action at each of the points. So each of these arrows, so this is a phase portrait or a phase diagram that represents the domain or the state space. And these arrows are the actions, the optimal actions to take at each of the state space to end up at this goal. That's with the red cross. And for that same problem, we can formulate this when we use trajectory optimization to solve it. We don't really care about all these other states. We just need a optimal state from that start state to that goal state. And so we end up with just this simple trajectory. And we can then give this trajectory to the robot to execute it. We don't really need to worry about what happens elsewhere. And so because of this, value iteration gives us a globally optimal sequence of actions to take or sequence of control inputs. But trajectory optimization is locally optimal because we don't really explore the whole state space. We only explore like a picked up region or a subsection of the state space, a subset of the state space. And so it's locally optimal, but then sometimes that's all we need to successfully perform a task. So, and it's also much less difficult to compute than value iteration because it doesn't consider the whole state space. It only considers a small state space. So that's the core difference between the two. So what's an optimal trajectory? So an optimal trajectory is basically the sequence of states and actions that the agent needs to take at each time to get from a start state to a goal state. So what's depicted here is basically a pendulum, and the goal is to get the pendulum to be perpendicular such that it's sitting at right angles to its cuts. So the trajectory here, the optimal trajectory here would be the trajectory that the tip of the pendulum moves through in order to end up at the goal states. And we could solve this using optimal trajectory optimization. And trajectory optimization is often formulated as an optimization problem, which has objective function, and we subject it to some constraints and dynamics that's based on that are based on the dynamics of the system you're trying to solve with. And so we make some few assumptions about trajectory optimization. So we assume the problem is a continuous time problem and has a single phase, in that we don't have to break at any points. We basically have a continuous time system where the system is continuous with respect to time, and it flows and there are no breaks. As a result, it's, yeah. And we also assume that, and there could also be situations where there are like discontinuities in a problem. For instance, if want to solve trajectory optimization for a walking robot, there could be discontinuities when the robot like steps on the floor, or like performs some discrete actions like steps on the floor or does something like that. For such situations, that stepping on the floor is a jump from one trajectory to another trajectory. So, or from one state space to another state space, sort of. And so there are ways to solve those problems, but in this slide, you're going to be focusing on continuous time single phase systems. So those systems are called like multi-phase systems because there are different phases, and one phase could be the robot's leg is in the air, and another phase could be the robot's leg is on the floor. But we only assume single phase systems here. And we also assume that all our dynamics, objectives, and constraints are smooth. And smooth means that there are no discontinuities anywhere, and they are differentiable everywhere. And consistent also means something similar, and they are probably nonlinear. But even if they're linear, it makes our work all the more easier. And we also assume that there are no functions like absolute values or minimums in the functions that describe the constraints or the objectives of the dynamics. And this is because absolute values and minimums use some if-else, and these if-else conditions cause discontinuities in the function because they cause like jumps, and we don't really need these jumps, because if we have these jumps, then methods for solving these trajectory optimizations are not going to work. So a trajectory optimization problem is made up of an objective function and constraints. So anytime you see objective functions and constraints, you know that this is an optimization problem you are trying to solve. And so the constraints, so the objective function is usually described in two ways. It's usually composed of two functions. So the first function could be the boundary objective function that basically specifies the start state, the end states, the start time and the end time. It basically specifies like what happens at the boundary conditions or the boundary points of our trajectory. And the objective and the integral cost function or the integral objective function basically represents like what happens along the trajectory. So the first describes what happens at the boundaries of the trajectory. The second describes what we want to happen at along the trajectory. And constraints are usually ways we are able to impose our preferences to the optimization algorithm in order to come up with solutions for us. So the goal of this trajectory optimization problem is to come up with these control variables. That's basically the states and actions, because a trajectory is basically just made up of states and actions. So all you want is to come up with a trajectory that's made up of optimal states and actions, where a state at time t, where these are all continuous, and because they're continuous, they have like this bracket and t. So anytime you see a function with brackets and t, a variable with brackets and t, it means that it's continuous. And so that's our goal, to come up with a trajectory made up of continuous states and actions that are optimal. And constraints are a way we can enforce our preferences to the optimization problem. So if you want to get a trajectory that obeys a certain system dynamics, you specify that as a constraint. And if you want to have a trajectory that avoids obstacles, like if you want to say, for instance, for a quadrotor, you probably want to avoid obstacles, and so you input that as a constraint to your optimization problem. And if you have some boundary conditions, that's like if the agency start at some states and end at some states, that could also be a boundary constraint. And if it's a finite horizon problem, then you'd also specify the start time and the end time. And if your controls, and if you want to also limit the torque or the control inputs to the system, you could also specify boundary constraints that basically specify what's the highest torque input or the highest control input you want to give to your system and the lowest control input you want to give to your system. And so applying all these constraints as well as specifying this objective function. An objective function could be made up of could basically describe any features you'd want the trajectory to have. For instance, if you want to optimize for fuel consumption in your vehicle, you come up with some additive objective function that basically minimizes the amount of fuel that's consumed. Or if you want to ensure that your trajectory is the shortest possible trajectory, you could also specify probably a sign distance function. You could also specify like the distance of the distance the trajectory takes as an objective function. So this is up to you to decide, as well as the constraints. It's also up to you to decide. So once you specify the objective function and the constraints, that's mostly that's like you've already specified your problem. So what's left is basically solving for the x of t and u of t that satisfy both the constraints and the objective function. And so most of trajectory optimization research is into coming up with ways of solving this optimization problem. And the generally agreed upon way of solving this optimization problem is basically to first discretize the time. And the reason why we discretize time is that they want to use nonlinear program solvers. So NLP solvers or nonlinear program solvers are a well researched field of optimization, and there are lots of very nice off-the-shelf solvers for nonlinear programs that can basically solve the nonlinear program and return some favorable outputs for you. And so trajectory optimization, basically most of trajectory optimization is basically coming up with ways of converting the optimization problem we specified here into a nonlinear program that can be solved by an NLP solver. And there are lots of ways of doing that. So an NLP solver is different from a trajectory optimization. It's different from an optimization problem in a key way. So the main difference between them is that an NLP solver considers only considers discrete time. It's not continuous time. An NLP solver can only solve for constraints that are discrete time constraints. And so we can't just present the NLP solver with this optimization problem that has integration and continuous functions, but have to come up with a way of discretizing the functions. And one major thing to note here is that this discretization is not the same as the one that's used for dynamic programming or value iteration. So in this discretization, the only thing we discretize is the time. We only discretize the time. We don't discretize the state. But then with dynamic programming and value iteration, they discretize the states, the entire state space. And so that's why their complexity increases exponentially with the dimensions. But with trajectory optimization, we only discretize time. And so by discretizing time, we can then get the corresponding states and then provide all of that to the discretized system, to the discretized time system, to the nonlinear program solver. And that basically solves the problem for us. And so most of the trajectory optimization methods deal with how to actually discretize the optimization problem into a nonlinear program. So some methods like the direct methods discretize first before they optimize. And by performing this discretization of the time before supplying it to the NLP solver to optimize, it becomes less accurate, but then it's much faster and it's easier to pose and solve. But then there are some other methods like the indirect methods that optimize first before they discretize. And It's probably more accurate, but then it's also harder to solve because they don't use NLP solvers. They use some other kinds of solvers, and that's a bit more difficult than the use of NLP solvers. And there are also other ways of and there are, so these are the various variations. And so once you after you solve the NLP problem, that's the nonlinear programming problem, it returns a discrete set of states and actions. And so given the discrete set of states and actions, it's now your duty to basically interpolate between these discrete set of points to come up with a continuous trajectory that you can then pass to your robot to actually execute it. So the sequence is like this. You first have a continuous states and actions you want to discretize. And then you first have continuous states and actions you want to optimize. And then you first discretize them into an NLP, and then use the NLP solver to return discrete states and actions. And you then interpolate these discrete states and actions to get continuous trajectories that you then pass to your robots to execute in the reward. And there are ways of performing interpolation. There are H methods and there are P methods. So H methods basically just increase the number of time steps you basically discretize your problem with. And by increasing these time steps, you basically come up with a much smoother trajectory. But then with the P methods basically perform the interpolation by increasing the order of the polynomial you use to perform the interpolation. So instead of say quadratic, interpolating using a quadratic spline, you can end up using a cubic spline or some fourth order spline. That's like much smoother, but then that's also much slower because you end up with much more complex splines. And so in the example we are going to consider, we'll basically be considering discretization using direct methods and H methods for interpolation. So a concrete example here is basically this optimization problem, trajectory optimization problem, where we want to come up with a sequence of torques or forces to apply to this cat pole or to this cat in order to get the pendulum from this down position to this top position. That's like to get it to be 90 degrees with the cat. And what kind of trajectory are you going to use? And mind you, the only force we are exerting is the force on the cat itself. We don't have any motor or actuator here at the joints of this pendulum. And so we basically rely on the dynamics of the system to basically come up with a trajectory to get it to be vertical. And so this is an under-actuated system because you're only controlling you're not controlling the whole system, only controlling a subset of the system variables. So how do we solve this? So in order to first solve it, we have to come up with the dynamic system, a description of the dynamic system, which would then pass it into the optimization problem as a constraint. And so from undergrad physics, we could actually describe this system using Newton's law, F equals ma, where we consider acceleration both due to gravity and due to the input force, and then would basically solve it. And so I'm not going to go into the details of this because it's mostly basic dynamics from an undergrad dynamics or physics course. But once you actually solve the system, you come up with these two equations that describe the system. And we can then end up describing the system in 4 parameters. So the first is Q1. So Q1 represents the position of the cat. And so these are all the state variables. So Q1 is basically the position of the cats along this one-dimensional plane. So we talked about this problem last week, so I'm just going to briefly describe it. And Q2 basically represents the orientation, the angular displacement of this pendulum. And Q1 dot represents the linear velocity of the cat, and Q2 dot represents the angular velocity of the pendulum state. And so a dynamical system would basically be described as x dot equals f of xu, where the f of xu is basically the derivative of x dots, which is basically the first and second derivatives of the variables, all the system variables. So having this dynamical system, you basically then describe our optimal optimization problem. So we come up with some objective function. So this objective function, it doesn't really matter. I guess it matters. It depends on what you want from your system. So if you want your system to have exact the least amount of torque, then you could describe an objective function like this. So this objective function is basically square root of u with respect to time, which basically says that we should minimize the amount of force or control inputs needed to stabilize the system as of in our final state. But then you could also specify, say, the trajectory should be shorter or something else. And the most important parts are like subject to these constraints. So this is a dynamics constraint that describes the dynamics of the system. We could also describe some inequality constraints like the boundary conditions. That's like the cat can only move from some position minus D to some position D. And our control inputs should also be from some minus U to some U. And these are the description of the parameters. And so this is basically a description of a trajectory optimization problem. And so having defined this optimization problem, the next step is to discretize it into a nonlinear problem. And direct transcription basically is the simplest form of discretization. So what it does is it comes up with a set of discrete times. So we want to perform this trajectory in some limited amount of time. So we basically specify from some time t0 to some t is equal to uppercase T. So in order to discretize it, we basically interpolate between these times. So we come up with a sort of time steps that are between the start time and the end time. And then given these times, we then use these times to discretize the states and the inputs as well. And given this discretization, we then formulate this as we then come up with some initial guess of the trajectory using this discretization, and we then pass it, and coming up with this initial guess as well as this discretization is then formulates it as a nonlinear program, which you can then use our NLP solvers to solve. And so this is the NLP problem, the nonlinear program problem. And so we notice that now we have instead of an integral, we have a summation. It basically tells us that it's now a discrete time problem where we have discrete states and actions. And it's subject to all of these discrete constraints, equality constraints and inequality constraints and boundary constraints. And these are some descriptions of the state variables. And because we have because we have inequality constraints, this ends up being a non-convex optimization problem. And so given this NLP, we then use our NLP solvers to solve this. So there are a bunch of NLP solvers out there like fmin-onc in MATLAB or SNOPT. So SNOPT or SNOPT is basically a commercial solver. So after having this description, basically just pass this description into the solver, and the solver then returns controls and initial and some state values that represent the trajectory. And what you need to do next is basically interpolate these points to get your trajectory. And how do we actually initialize the NLP? So as I said earlier, the NLP needs some initial trajectory to start with, because that's what most optimization algorithms need. They need some initial guess, and given the initial guess, they can then perform optimizations on this initial guess to come up with an optimal trajectory. And for most problems, it's a more systematic way of coming up with the initialization for NLP is to solve an easier problem and then use that solution for that easier problem or that simple problem to initialize the NLP. But for the cat-pole problem, because it's a pretty simple problem, we could use a straight line as our initial guess. So so this is basically a straight line from the start states to the end states, and that's basically our guess, and it's represented by this function. And given this initial problem, you can then give this to the NLP solver as well as the NLP description, and it's going to solve for states and actions, optimal states and actions. And it doesn't really matter the quality of the initial guess, at least for this pendulum problem, this catpole problem. And so this in orange is our initial guess, and the NLP solver solves for, an NLP solver returns some positions and orientations, sorry, positions, orientations, and some controls, some control inputs. And so because we presented the NLP solver with a discrete problem, it ends up with, it returns these discrete set of points. That's basically represent our trajectory. And the next step would be to interpolate between these points to come up with a smooth trajectory that solves our problem. And so, yeah, it returns these discrete points for both the states and the control. So this is basically our optimal trajectory sort of, but it's discrete. So the next step would be to interpolate between it. And then there are various methods for interpolation. You could use a quadratic spline that basically comes up with a quadratic function between consecutive points. Or we could use a cubic spline that's basically much finer. And so usually the way you interpolate is that the interpolation for the state should be an integral of the interpolation for the control. Meaning, if you use a cubic spline to interpolate the states, you have to use a quadratic spline. That's a derivative of that cubic spline. That's a quadratic spline to interpolate the control inputs. But if you use a quadratic spline to interpolate the states, you'd have to use a linear spline. That's basically lines between consecutive points to interpolate the states. And there's a more mathematical derivation, mathematical reasoning for this. And I'm not going to go into that. In the original slides, they went into that, but that's not that important. So I'm going to skip it for now, but I could add a link to the original presentation if you're interested in that. So that basically describes what trajectory optimization does and how it's able to come up with optimal trajectories. So yeah, going back to our slides. So right now we've already come up with a way of returning optimal trajectories from some initial states to some goal states. But then the problem with trajectory optimization is that looking at this system, we basically have a trajectory that basically tells us that if we at any point along this line, we can then take some action that's also along some line. But then what if we end up in a state that's not along this trajectory? What are we supposed to do? And this is going to be often the case because in the real world, there's a lot of noise. And even if you give a vehicle, if you're trying to control a vehicle, even if you give a vehicle the control to end up at some state, it's probably going to miss most of the time because of friction in the ground, as well as some other noisy artifacts of the real world. And so what we basically need to do is come up with a way of replanning or reperforming this trajectory optimization at every point, or come up with some way of robustly performing trajectory optimization in order to perform a real world task. And that's where model predictive control comes in. So model predictive control is basically replanning. So if you've done a lot of robotics research, or if you work in planning, model predictive control is just like, it's the same as planning, but then it's the same as replanning, but in the context of controls. So how it works is that you first measure the initial state of the system, and then you perform trajectory optimization from your current states to some goal states. And then you end up with a trajectory that's represented like this. And then what you do is you don't execute the full trajectory, you just execute the first action from the trajectory or some finite action or a subset of the whole trajectory. You execute that, and then you throw away the rest of the trajectory, and then you let the dynamics evolve. For instance, if you're a vehicle, you input only the subsection of the control inputs, and then you let the vehicle move. And then after that action is executed, you then repeat the whole thing, you then replan. So by performing this constant optimization and replanning, the agent is going to be able to actually successfully accomplish tasks in the real world And MPC, model predictive control, is used right currently in almost almost all complex systems like legged locomotion systems and quadrupeds and all that, because of its niceness. So if you have a trajectory optimization that's like extremely fast, like if your optimization is really fast, then you can actually perform MPC online. So you move from some start state to some goal state. And there's a video from Georgia Tech that uses MPC to get a robot to get a self-driving car to race on some track. I should have added it into in the slides, but I totally forgot about it. But it's pretty cool. So if your trajectory optimization is really fast, then you could use MPC to get your system to act correctly or to perform the task you want it to perform. And yeah, so that's the whole idea about MPC. And so the way of optimizing the trajectory, you don't just have to use trajectory optimization. You could also use like different methods like iterative LQR, which is basically LQR, but then performs it iteratively. That's basically linearizes the system at multiple points. So for instance, if you want to use LQR, iterative LQR with an MPC, you first linearize your current position, perform the optimal control, and then you linearize again, and then execute it, linearize again, and execute it. Perform that multiple times to end up at your goal state. And so MPC is like this general framework with which you can do lots of interesting things. And I actually think that replanning in robotics or in robot planning was basically gotten from this idea of model predictive control. And so it doesn't really matter the quality of the model you use. You could use terrible model, but because you're basically replanning and re-optimizing at every step after taking every action, it makes you much more successful. And you might think, oh, MPC seems very hacky, but there are lots of theoretical results on MPC and optimality analysis and all of that stuff. So if you're really interested in finding out whether MPC is actually something legit or whether it's just engineering hack, then you can actually look into it. But as far as I know, it has some really good theoretical results and feasibility results. And so this is an example of MPC working on a simulated vehicle. And this video was from the Udacity's self-driving car non-degree program. So this assignment was basically to develop an MPC for an autonomous vehicle that's able to follow some trajectory to constantly replan or reperform trajectory optimization and then follow that plan. As you realize here that the green line from the vehicle is the plan that's being generated from using trajectory optimization, and then it keeps replanning every time the action is taken. And because it's really fast, it works like very cool. It works very fast, and it's pretty successful at getting the robot to drive around. And so the last topic we'd like to talk about is basically differential flatness. So differential flatness is a way of converting non-convex problems into convex problems using some clever change of variables. And so for some systems, if you have, you can specify the trajectory using just a subset of the entire state variables that are used to describe the states. And then because of the way the system's equations are, you can then infer the other variables you need to actually execute the trajectory in the real world. So for instance, this is a system dynamics equation for the planar quadrotor. So the planar quadrotor is basically a quadrotor or a quadcopter that's in a planar region. That's basically like a 2D quadcopter. And these are the system dynamics equations that can be used to describe it. So its degrees of freedom are x, y, and theta, meaning it can travel in the x direction as the horizontal, the y direction, as well as orient itself in some theta. And there's the system dynamics to describe it. But the nice thing about this is that, about this combination of the system is that if you're only giving a trajectory that's with respect to just X and Y, for instance, if we want to we want to solve for an optimal trajectory like as quick as possible, we can then describe the system in just X and Y. We could like forget about theta and all that stuff and U or whatever. We could just describe the system in terms of X and Y, and we could use an extremely fast priority optimization solver to solve for optimal trajectories for in the X and Y. But because of this equation, if you're able to get some smooth X and Y functions that describe the optimal trajectory, you can use this equation or the formulation of this equation to derive the respective theta, that's the orientation, as well as the control inputs U1 and U2. So control inputs U1 and U2 the control inputs U1 and U2 basically represents the control torques or the control inputs to the two actuators that's basically control the motors for the quadrotor. So U1 is for the first motor, and U2 is for the second quadrotor. It's for the second motor. So if you have X and Y, we could basically use this function, this fraction equals tan theta to derive theta. And once we have theta, we can then infer the U1 and U2 using this system of equations. And this is really nice, and this is like a neat trick that makes it very easy to perform extremely complex trajectories optimization with just a subset of the state variables. And this trick was used, there's some code example on how it's performed using this 2D planar quadrotor, but I'm not gonna go into the code. I'm just gonna show you the outputs. So once you run the code that's on that link, you end up with this trajectory where well, even though we only plan in terms of X and Y, because we use differential flatness, the differential flatness strip, we can then infer the orientation of the quadrotor that can like move through obstacles as well as moving X and Y directions. And so that's a 2D example. And for a more convincing example, we could use this video from Vijay Kumar's lab. So in this video, they basically perform differential flatness with a 3D quadrotor. So here the state is XYZ, and I think theta. I think it was it just theta? Nah, I'm pretty sure it was like rho pitch yield. So it has a 6 degree of freedom states, but then because of the way they describe the state dynamics, we can just plan a trajectory in terms of XYZ, which is pretty easy to do. And you could even use a regular motion planner like say RLT to plan this XYZ trajectory. You might not even need chart optimization. But then the nice thing is that once you have this trajectory, we can then use the equations, system dynamics equations, to infer the control inputs to each of the 4 motors, as well as the rho pitch yield orientations that are needed to perform these aggressive maneuvers. And so that's ultimately what they actually use in these really nice demos. I think this demo is probably like 10 years old right now, probably 10 or 12 years old. And this was what inspired most people to enter into autonomous flying research. And I think this was like really, really cool. I always find it really interesting when people use quadrotors to perform like really interesting maneuvers. And so, yeah, this is my last slide. So are there any questions anyone wants to talk about? I can just replay this over and over again. So that's the end of the optimal control tutorial. I mostly did this tutorial because I was really interested in optimal control, and I realized that most of our research is mostly high level, and we mostly assume that we have some controller that's able to execute our plan and all that stuff. But then it's important to actually know exactly how these things work, because the tools that they use in these regions, these are very well studied subfields of robotics, and so by learning these tools and the optimization methods and the way they frame problems, it could inspire us to create much more well-performing algorithms. So that was my main motivation for going through this tutorial series. And yeah, so this is the last slide of the last tutorial. So if you have any questions or anything you want to say, the floor is open. Yeah, but if not, thank you all for coming. I should probably stop the recording. Thank you, everyone. And yeah, see you next time. So next week, I think Nicola is going to be presenting. So I'm looking forward to that. Thank you, everyone. Bye.